Welcome to the continuation of oxides and salts. So in the previous video we looked at oxides and also looked at salts. We looked at types of oxides and also types of salts. In this video we're going to concentrate on preparation of salts. So now this topic, preparation of salts, is going to be delivered into two videos, this one and the next video, which is going to be the last video on oxides and salts. So on preparation of salts, we're going to first take a look at some terminology. So there are certain compounds, certain types of salts that that we need to know about. Then after that, we're going to take a look at preparation of salts, how salts are prepared, part 1, which is of course the main essence of this video. Then the next video is going to concentrate on preparation of salts, part 2. So we'll start with the terminologies. So these terminologies is not like some terminology that we're going to be using in understanding the preparation of salts, but they are more like some types of salts that have got certain properties which we need to know as students of chemistry. So the first type of salt is hydrated salt. Hydrated salt. So remember, we talked about the types of salts, normal salts and acidic salts. So those are not the types of salts we're looking at here. These are just special types of salts that have certain behaviors that we're studying. Okay? Hydrated salt. So usually when you see the word hydrated, it talks about having water. When you drink water, they say you are hydrated. And when you don't have water, they say you are dehydrated. So hydrated salt is just a salt that has water in it. So hydrated salt can be defined as a salt that contains water of crystallization. The question is, what is water of crystallization? So the way hydrated salt is they contain a fixed amount of water in their crystal lattice. What does it mean? Remember when we talked about crystals, a simple example of a crystal is a cube of salt. So a single cube of salt, it's roughly a good example of a crystal. So the way hydrated salts is they have a crystal for salt, for example, sodium and chloride, which is the common salt. We have sodium and chlorine atoms connected. Then somewhere there's some water that was left due to crystallization. Or due to the process of crystallization. Remember, the process of crystallization involves coming up with crystals from dissolved solutes. So those solutes, when they are when the solution is being heated up so that the water evaporates and we remain with crystals, there's some water. There's some water which is trapped inside the crystals, and that is water of crystallization. Hope you are able to picture that. So in short, water of crystallization is just the fixed amount of water in the crystal lattice. So like I said, the water of crystallization is part of the structure. That is just an emphasis. So if this water is removed, if the water of crystallization is removed from the crystal by heating, for example, the color and shapes of the crystals may change. Okay, so when you remove that water, the color can change. For example, if it is blue, it might turn into another color, and also the shape might change. Usually they might end up becoming powdery. So that's all about hydrated salts. So here are examples of hydrated salt, and this is how you can tell that this is a hydrated salt. So I've got copper 2 sulphate 5 water. That's the name. So its chemical formula is copper sulphate, of course. Then it has 5 water molecules. We have sodium carbonate 10 water, which is this. We have cobalt 2 chloride 6 water, which is this. We have iron 2 sulphate 7 water, which is this. The second type of salt is anhydrous salts. So anhydrous is a salt that is dehydrated, so to put it, or that doesn't have its water of crystallization. In short, anhydrous salt is a salt which has lost its water of crystallization. Okay, so when a hydrous salt loses its salt of crystallization, it becomes anhydrous salt. So when water is added to anhydrous salt, then the salt becomes hydrated. It becomes a hydrous salt, a hydrated salt. Okay. So in short, anhydrous salt is meant to have some water of crystallization, but it has just lost it. So when you add water to it, it can go back to a hydrated salt. So this is a hydrated salt. So this hydrated salt, due to maybe heating, it can lose its water of crystallization and it can form the copper sulphate and water here. Okay, because this water is the one that was near, so it has been lost. So this salt, if initially it had water like this, then it is anhydrous salt. So if you look at the states here, initially it was blue copper sulphate. Remember what we said when we were talking about hydrated salt. When they lose water, they can change the color and structure. So copper sulphate 5 water, copper 2 sulphate 5 water is blue in color, and when it is heated, it loses water, it becomes pale blue and it becomes powdery. From being a crystal, it becomes powdery. So the powder is because it has lost its shape. So this connects what we discussed in the previous type of salt, which is hydrated salt and anhydrous salts. So the opposite is true. If you take copper sulphate, copper 2 sulphate, you add water, that is 5 molecules of water, then it's going to become a hydrated salt and the heat is going to be released. Remember, for this, heat was added, but for the opposite process, heat is going to be released. And the color, of course, will change from pale blue, and it was powdery, to blue copper 2 sulphate crystals. So this process of adding water to change something is called hydration. Then the third type or third term we're going to take a look at is efflorescence. Efflorescence is just the loss of water of crystallization to the atmosphere. So in the previous example, when a hydrated salt becomes anhydrous salt, what happens? We call it efflorescence. So another good example is this one, which has sodium carbonate with 10 water. So in this one, a part of water of crystallization is lost. So it will be sodium carbonate with 1 water, and 9 water molecules are going to be lost. So this is efflorescence. Then another term is deliquescence. So this is the absorption of water from the atmosphere to form a solution. So there are some substances that have a tendency of absorbing water from the surrounding. So such substances are said to have the property deliquescence. So a good example is calcium chloride. So calcium chloride is a deliquescent salt because it absorbs water from the external environment or from the atmosphere. Because of that, it is used as a drying agent in what is called a desiccators. So a desiccator is an apparatus that is used to dry substances. So if you have put something that is wet, that has water, you put it in a desiccator, then the water is going to be absorbed from it. So calcium chloride is used because it has a property of absorbing water. So this is all about deliquescence. So like I said, the desiccator is just a piece of equipment used to dry substances. 5 we have got, I think this is the last term. Yes, it is the last term. It's hygroscopic. So what does it mean? A hygroscopic substance absorbs water from the air but does not change its state. So the difference between deliquescence and hygroscopic is in deliquescence the state changes, but hygroscopic, it absorbs but its state does not change. What do I refer to by state? I'm talking about being a solid, liquid, gas. So in hygroscopic, a substance will be able to absorb water, but its state won't change. If it's solid, it will be solid. If it's liquid, it will be liquid. If it's gas, it's going to be gas. But of course, we're talking about solids here. So it's a solid which when it absorbs water, it does not change. So a good example is anhydrous cobalt chloride. So how so? So anhydrous cobalt chloride, it of course doesn't have its water of crystallization, and it is in a solid state. So if you take this anhydrous copper 2 chloride, which is of course copper chloride without water, then if there are 6 water molecules in the surrounding, it will absorb these water molecules, forming the hydrated copper chloride. But the state won't change. It's solid, it will still be solid, and heat is going to be released. So if you look at the states, the colors, copper chloride is blue, and when it absorbs water, it's going to be pink. So the color changes, but the state does not change. Okay. So one thing also to note here is the fact that when you put copper chloride in somewhere where there is water, it changes its color. So this can be used as a test for the presence of water. So if you want to test if something has water, you put copper chloride. What's going to happen is the copper chloride is going to change color from blue to pink. Then you can tell that there is water here. So in short, the reaction is often used as a test for the presence of water. This process can also be reversed by heating the pink hydrated salt. So if you heat this pink hydrated salt, it's going to give you these two. So this is similar to what happens to when you have hydrated salt, it becomes anhydrated, and anhydrated becomes hydrated. So this shouldn't be something new. So this is the reverse process. Copper chloride, hydrated copper chloride becomes copper chloride with water, and pink of course blue. Now we start preparation of salts. So here you're going to acquire a special skill which is going to give you the ability to make decisions on how a salt can be prepared. So pay attention. So the method chosen to prepare a given salt depends on its solubility and how it can be separated from the mixture of other products. So solubility, we talked about solubility of salts. We talked about salts which are soluble and salts which are not soluble. So based on the solubility, you can tell the method that you are going to use to prepare a salt. Also, when that salt is prepared, you have to separate it from whatever mixture it's going to be in. So the solubility and the method of separating from the mixture matters. Okay. So with that being said, what are the different ways in which you can prepare salts? So there are basically 4 methods of preparing salts. The first is called synthesis. This is very simple, as you're going to see. The second is called replacement or displacement. The third is called precipitation or double decomposition. Then the fourth is called neutralization. So we're going to start with synthesis and displacement or replacement. Then in the next video, we're going to take a detailed look at precipitation and neutralization. So this is synthesis. So I've just put everything here so that you see, but follow me. So synthesis is the method. This method involves the direct combination of elements for binary salts. So a binary salt is a salt that has 2 elements in it. For example, sodium chloride. Sodium chloride. So sodium chloride is a binary salt because it has sodium and chlorine. Okay. So what happens in synthesis? So what happens is a salt is prepared directly from its elements. So for example, sodium and chlorine. You take a metal, which is sodium, and chlorine, which is a halogen. Okay, group 7 elements, remember, are called halogen. So you combine a halogen and a metal direct. If you can combine them, then you have sodium chloride. Okay, so the equation is always simple. Metal plus halogen is equal to salt. So example is preparation of iron 2 chloride. So iron 2 chloride can be prepared by passing chlorine gas over heated iron. So you get iron, you heat it, then you pass chlorine there, the chlorine gas, then you are going to have salt which is to have a salt which is ion 2 chloride. So this is ion, which is of course solid. You heat it, then you pass chlorine gas there. What you're going to get is ion 2 chloride. So this is how it is prepared. And you can come up with other examples. You can talk about potassium chloride. You get potassium and chlorine, you combine them directly. So that is synthesis. The second one is replacement or displacement. So this one we studied it when we were talking about acids and bases. So remember, we had talked about the reaction of acids with metals that are more reactive than hydrogen to form a salt and water. So is it an hydrogen? Anyway, so this is a method where the hydrogen ions in an acid are replaced by a metal. Okay, so but this metal must be more reactive than hydrogen on the reactivity series. It can also be defined as a reaction in which one element displaces another from a compound. So what we have is a reactive metal reacting with acid to form salt and hydrogen. Okay, so in this acid, the hydrogen in the acid is going to be replaced by the reactive metal. Okay, by a reactive metal, I mean a metal which is higher in the reactivity series than hydrogen. So when that reactive metal replaces the hydrogen is going to come out. That's why it's sometimes called displaces, because hydrogen is being displaced by the reactive metal. Okay, so this is replacement. So here is an example of a replacement reaction. So we're going to see the procedure. You have to note all the points, because sometimes you can be asked to describe the procedure of what to prepare a salt using replacement or displacement. So we're going to prepare iron 2 sulphate. Okay, so this is possible. In an exam, they can ask you, how do you prepare iron 2 sulphate? So I've got this salt iron 2 sulphate. So what's the thinking? What you need is where to get the sulphate and where to get the iron. Okay, so you ask yourself, where can I get the iron? There are two methods. The first method maybe that you can think of is synthesis, but you have to ask yourself, synthesis needs iron and also maybe a halogen. Okay, iron is a metal. You need the metal and the halogen. So a metal, you have it, it's iron, but a halogen, sulfate is not a halogen, so that cannot work. So you think of replacement, but replacement, you need an acid that has got sulfate. This should come from an acid. So yes, we can have sulfuric acid, but the metal has to be higher in the reactivity series than hydrogen. So you ask yourself, can iron be higher in the reactivity series than hydrogen? Yes, it is. If this was something like gold or silver, then of course it's not possible, because silver is lower in the reactivity series than hydrogen. So since iron is higher, so yes, it's possible to use replacement reaction. So what's the procedure? So the procedure is simple. First, you add iron fillings. You add iron fillings to home dilute sulfuric acid in a beaker until no more hydrogen gas is evolved. So you add bit by bit. You add the bit, then when you add, there's going to be a gas evolving. Then you can keep on adding till there is no more gas evolving. So when you add a bit of iron fillings, what happens? The iron fillings reacts with the dilute sulfuric acid, and hydrogen is produced. So the bubbles that are going to come out, actually, it's hydrogen. So you have to keep on adding. When you add in, it shows that the reaction is happening. You reach a point when there's no more hydrogen coming out. So when that happens, it means all the sulfuric acid, all the molecules of sulfuric acid in that acid have been used up. So there is no more reaction. So if you keep on adding, there is nothing you are doing, because there is no any reaction. So when you do that, what next? The next is to remove the excess iron. Remember, you were adding till the bubbles were no longer forming. Okay, so the additional iron fillings that you added are nothing but just excess iron fillings. So you need to filter them off. Okay, so you need to take a filter, a filter paper, then you filter off the solution, so that the excess ion fillings can be removed. So this is the reaction. So these are the two steps that you should have in your heart when you are using this method. So here we have iron, which is solid, and sulfuric acid. When they react, iron is going to take the place of hydrogen here. So it's going to become iron sulfate, and hydrogen is going to be evolved. So this is displacement. So there are two things to note which I have already mentioned. First, iron should be in excess so that all the acids is used up. Second, air must be excluded to prevent oxidation of iron to sulfate. So this one actually I did not mention. So when you're doing this experiment, keep the iron away from air, because iron can react with oxygen, which is in the air, to iron oxide, which is the oxidation we're talking about here. So air must be excluded to prevent oxidation of iron to sulfate. Actually, it's not the iron but the product, which is iron to sulfate. It can be oxidized. So this marks the end of this topic. It has taken us 21 minutes, which is kind of the longest I've created in a while. Anyway, hope you have enjoyed. Make sure that you assimilate all the information here as we look forward to the last part of preparation of salts, which is actually very important. Happy solving.